In this video, we look at grade 12 identities. Now, we have worked with identities before, but what changes in grade 12 is the inclusion of double angles and compound angles in the identities. So, when we prove an identity, we have to prove that the left-hand side of the equation is equal to the right-hand side. Now, to prove that, remember that you have to split up the left-hand side from the right-hand side. So, then you work with one side and you manipulate it to show that it is equal to the other side. Whether you start with working with the left-hand side or the right-hand side is up to you. Sometimes you might have to work with both sides and simplify both sides to show that they're equal to the same thing. Remember to always draw a conclusion at the end of your proof to say that the left-hand side is indeed equal to the right-hand side. The second thing that I want to just summarize is the tools that you have. Okay, now we have the grade 11 identities. So the quotient identity, tan theta is equal to sine theta over cos theta. We have the square identity, sine theta squared plus cos theta squared is equal to 1. We now have the double angle formulae, the compound angle formulae, and what we will also use in the proof of the identities is some algebra. So when you are adding or subtracting fractions, it is a good tip to try write it as one fraction with the lowest common denominator and simplify. The second algebraic tool that you must remember is that you can factorize. And remember all the different forms of factorization. Highest common factor, difference of squares, trinomials, grouping, sum or difference of cubes. Okay. Right, then I just want to give you a tip about identities involving double angles. Now, if it is a sine double angle, it's simple because there's only one expansion form of a sine double angle. But if we have a cos double angle in the identity, cos double angle can expand to 3 different forms, okay, which makes life a little bit more complicated because we need to decide which form to choose. Okay, so use this tip. If the identity contains a cos double angle, choose the option that eliminates the constant. Okay, so if, for example, you had 1 plus cos double angle in your identity, you would choose the option that would get rid of this 1. So you would choose the option that would have a minus 1. That means we would use the 2 cos a all squared minus 1 option. That means the 1 minus 1 eliminates the constant and we are left with a simplified form. Okay. If, however, my identity contains cos of a double angle minus 1, I need to choose an option that would eliminate the negative 1. So I would need the expanded option that has a positive 1, which is the 1 minus 2 sine of the angle all squared option. So I substitute 1 minus 2 sine a all squared in place of cos 2a, and then the positive 1 minus 1 eliminate each other, and it simplifies without a constant. Now, we are going to work through 3 examples of proving different identities. Okay, so the first example says, prove that 1 plus cos x plus cos 2x over sine 2x plus sine x is equal to cos x sine x. Now, the first thing you want to look at is the angles. Notice that although we have x everywhere, some of the angles are double angles, while others are not. Okay, if they were all double angles, we might not have to expand the double angles. But because not all the angles are double angles, we know that we will have to expand. Okay, so I'm going to split up the left-hand side from the right-hand side. And because the left-hand side happens to be the most complex, I'm going to start with the left-hand side. So I write it out and I begin. Now work with the numerator and the denominator separately, so in turn, okay? In the numerator, I have 1 plus cos x plus cos 2x. Now the first thing I'm going to do is expand the double angle, okay? Now I've got a cos double angle, which gives me 3 options of expanding it, okay? So I need to be very wise in choosing which option to expand the cos double angle to, okay? Now, I have a constant of 1 in the numerator, so I would like to choose an option that would have a negative 1 in order to eliminate the constant. So I'm going to choose to expand the cos double angle using the 2 cos of the angle all squared minus 1 option. So I have 1 plus cos x plus 2 cos x all squared minus 1. Then I look at the denominator and I have a sine double angle, and there's only one way that can expand, and it's 2 sine x cos x. Then I still have the plus sine x. Right, now all my angles are just x. So I simplify the numerator. 1 minus 1 is 0, so I'm left with cos x plus 2 cos x all squared, and that is over 2 sine x cos x plus sine x. Right, now I have a fraction. Now to simplify a fraction, I would like to cancel common factors between the numerator and the denominator. But in order to be able to cancel factors, I must have one term in the numerator and one term in the denominator. Currently, I have 2 terms in both. So to make those 2 terms into one term, I factorize. Okay, so in the numerator, I have 2 terms, cos x plus 2 cos x all squared. Now, if I look at those 2 terms, the first factorization I'm always interested is whether there is a common factor. Remember that cos x all squared means cos x all squared like that, which is cos x times cos x. Okay, so the first and the second term have a cos x in common. So I'm going to factorize out the cos x, which is like dividing it from the term. So then in the first term, I'm left with cos x divided by cos x, 1. In the second term, I have 2 cos x all squared. If I divide it by cos x by factorizing it out, I'm left with 2 cos x. Right, in the denominator, I have 2 terms. Looking for a common factor, I find that they both have sine x. So I can factorize out the sine x, and I'm left with 2 cos x in the first term, plus in the second term, if I factorize out the sine x, it's like dividing. So sine x divided by sine x is 1. Okay, now I have one term in the numerator and one term in the denominator, so I can cancel any common factors. Now, if we look at the brackets are not identical, but they have the same value. The only difference is that the terms are in a different order, but the order of terms doesn't matter. As long as I take the sign in front of the term with it. So I have a positive 1 in the numerator, positive 1 in the denominator bracket, and a positive 2 cos x, positive 2 cos x. So those brackets are identical, and I can cancel them out, and I'm left with cos x over sine x, which happens to be the right-hand side. And I finish my proof of the identity by writing that equals right-hand side. If we look at the second identity, it says prove that, and we have 1 minus cos 2x over sine 2x equals tan x. Now, if we look at the left-hand side, the angles are the same. I've got 2x and cos 2x and sine 2x. So I might be tempted to think, oh, okay, the angles are the same. I don't have to expand. But if I look at the right-hand side, I notice that I don't have that 2x angle. I have x. And that indicates to me that I must expand those double angles. So I'm going to work again with the left-hand side. So I have 1 minus cos 2x over sine 2x, and I'm going to expand. Working with the numerator first, I have 1 minus. Now I need to decide which option to expand the cos double angle to, okay? And I want to choose the option that's going to eliminate the constant. So my constant here is a positive one. So I want to subtract 1, okay? But be careful. This negative in front of the brackets will change the sign of the constant inside the bracket. So I want a positive one inside the bracket so that this negative times the positive gives me -1, which eliminates the first term's positive one. Okay, maybe when you see this, it'll make more sense. So I'm going to choose this last option here. Okay, so cos double angle, in this case, I want it to expand to 1 minus 2 sine x all squared. Okay, so what I said is that I'm choosing the positive one inside the bracket because the negative, which is distributed inside the bracket, will make that -1, which eliminates that initial one. Okay, now this will seem obvious, but don't forget about the denominator. Okay, I see it so often that students get so engrossed in working with the numerator that they now would just carry on working with the numerator and the denominator just disappears. And then they wonder why they can't finish the proof. Okay, so be very focused in your work here. So, working with the denominator, I have sine 2x, and that's easy. We know it goes to sine x cos x. There is no other option. Okay, simplifying the numerator, I have 1 minus 1 plus 2 sine x all squared over 2 sine x cos x. That simplifies to 2 sine x all squared over 2 sine x cos x. Now I have one term in the numerator and one term in the denominator, so I can cancel factors. Okay, now just for those that need this, I just want to show that the sine x all squared is sine x times sine x. Okay, so this makes it very clear what I'm going to cancel. So I'm going to cancel the 2's and I'm going to cancel the sine x's. So I'm left with sine x over cos x, and from the quotient identity we know that that is equal to tan x, which is the right hand side, and I finish by saying equals right hand side. In this third and final example, we have to prove that sine 2x minus sine x over cos 2x plus cos x is equal to sine x over cos x plus 1. Okay, so first thing we look at is the angles, and we notice I have some x's and some 2x's. That means I have to expand the double angles. So again, here I'm going to start with the left-hand side. But now, just because my 3 examples have started with the left-hand side, don't think that that is always the case. Sometimes you'll have to start with the right-hand side. Sometimes you'll have to work on both sides. Okay, so sine 2x minus sine x over cos 2x plus cos x. Working with the numerator first, I have a cos double angle that expands to 2 sine x cos x, and then I still subtract the sine x. Looking at the denominator, I have cos double angle x, okay, so cos 2x plus cos x. So I need to expand this cos double angle. Now, the tip I gave was to choose the option that eliminates the constant, but there is no constant in the denominator, so that tip is not going to work for this example. Okay, so the second tip is choose the option of the cos double angle formulae that avoids introducing another trig function. Okay, so avoid introducing another trig function. In the denominator, that is here. Okay, so y, we will have to later factorize the denominator. Now, if I introduce another trig function like sine, for example, it'll become very difficult for me to factorize this. So if I keep to just cos x, okay, why? Because there is another term with a cos x in the denominator. If I stick to just having cos x's, the factorizing will be a lot simpler and doable. Okay, so I'm going to choose the second option here for the cos double angle expansion because it has only cos x function. So it's 2 cos x all squared minus 1. And then don't forget to add the cos x, okay? Plus cos x. So easy to drop one of the terms along the way because these things are so complex and there's so much detail. So stay focused and check every step. Okay, so now we are going to have to factorize our numerator and denominator because we want to simplify. To do that, we have to cancel common factors. Okay, so if I look at the numerator, I've got two terms. And among those two terms, I have a common factor of sine x. So I'm going to factorize out the sine x, and I'm left with 2 cos x minus sine x divided by sine x is 1. If I look at the denominator, you see something scary, okay? But it is a trinomial, okay? Now, if you don't like what it looks like, substitute in place of the cos x a variable, okay? So that you can see the trinomial more clearly, okay? So we're going to say let you choose, but I'm going to say k equal cos x, okay? So then I have 2k squared minus 1 plus k. Okay, and immediately we can see more clearly how this trinomial works. So I'm going to write it in standard form. So I've got the k squared term first, then plus k, then minus 1. And this is a lot simpler to factorize than the trig version of it. Okay, so I'll have 2k in the first term in the first bracket times k. Then I'll have 1 and 1, and I just need to decide on the signs. So outers and inners must add to give me positive 1. So I want positive 2k minus 1k. Okay, so what I write in my working is the cos form of this. So I'll have the two brackets, and I'm going to, in place of k, substitute cos x. So I have 2 cos x minus 1, and then cos x plus 1. Okay, right, now I have one term in numerator and the denominator, so I can look for common factors to cancel, and we see we have a whole bracket in common. So I'm left with sine x over cos x plus 1, which happens to be the right-hand side. And that is the end of our proof.